Hello friends. So today we are going to do questions from the year 2016 and there are total of 7 questions, and it's a mixture of mains plus advanced. So the first question, it was asked in the 2016 mains, and it states that in an experiment for determination of refractive index of glass of a prism by I delta plot, it was found that a ray incident at the angle of 35 suffers a deviation of 40 degree and that it emerges at an angle of 79. In that case, which of the following is the closest to the maximum possible value of the refractive index? So we are basically given that the angle of incidence is 35, deviation, that is our delta, is 40 degree, and angle of emergence is 79. So here we are going to use, you can say, basic two formulas. One is about the Snell's law and other is the relationship between our angle of incident and our angle of the prism and the delta. So you can say that if mu is the refractive index of the prism, so you can say refractive index of prism, if it is given as mu, then by Snell's law we can write that our mu is equal to sine of I upon sine of r, and we know that our I is equal to a plus delta m divided by 2 and r is equal to a by 2. Okay. Therefore, we substitute them, we get this as sine of a plus delta m divided by 2, and this is our sine of a by 2, and where a is the angle of prism and delta m is the minimum deviation through the prism. Okay. So here delta m is the minimum deviation. Okay. And a is the angle of prism. Angle of prism. And we already know that the values that are given to us, we are given that incident angle is of 35 degree and deviation, that is of delta, it is given as 40 degree, and angle of emergence, that is E, is given as 79 degree. Okay. And we also know the general relationship between the delta, and we can write that angle of deviation is equal to I plus E minus A. So from here we can easily find out our angle of prism, that is our A. Delta is our 40 and I is our 35 plus 40 and minus 79. 79 and minus of A. So this gives us that A will be coming as 74 degree. Okay. And we also know that this angle of prism can be written as R1 plus R2 is equal to A, which is equal to our 74 degree. And refractive index is given to us, therefore we can write that our refractive index is 3 by 2. Oh, okay, we need to find out the value of refractive index. Okay, so we are going to put all the respective values and try to sort it out which will be the correct one. So we are going to take the option A, which gives us the mu is equal to 1.5. So therefore we can write that 1.5 is equal to sine of A we just found out is of 74, and this becomes of delta m divided by 2, and this is our sine of 74 divided by 2, and this can be written as, this will be coming as sine of, this comes as 37 plus delta m by 2, and we have sine of 37, and sine of 37 is close to, you can say 6.6 rather, okay, and say 0.6 multiplied by 1.5, so this gives us 0.9 will be equal to sine of 37 plus delta m divided by 2, and this 0.9 is approximately equal to sine of 64. So we can write this as that our sine of 64 is equal to sine of 37 plus delta m divided by 2. So this gives us that 37 delta m divided by 2 will be equal to 64. So therefore delta m is approximately equal to 54 degree. Okay. And this angle, you can say, is greater than the deviation angle which is given to us. So it means for a greater mu, the deviation will be even higher. So if we, because this is the minimum deviation, so we can say delta m is our 54 degree, and this is our minimum deviation. And if we check all the rest values of mu, so all the rest values of mu are greater than 1.5. This is 1.6, 1.7 and 1.8. Okay. So it means if mu is going to increase, so we can say if mu increases, this will further result in increase in the deviation. Okay, so you can say deviation increases. Okay. Therefore, the refractive index, that is our required mu, should be less than 1.5. Okay. Or we can say this mu should be approximately equal to 1.5, because this value is giving us a minimum value of our delta m, that is 54. For all other values of mu, which are our 1.6, 1.7 and 1.8, the deviation will be greater than our 54. So you can say delta m for all these values of 1.6, 1.7 and 1.8 will be greater than 54. So therefore this is our minimum value, closest is 1.5. So option number A is the correct one. Option A is correct. We go to the next question. It was asked in the year 2016 in advance, and it states that a parallel beam of light is incident from air at an angle alpha on the side PQ of a right angle triangle prism of refractive index n is equal to 2. Sorry, it has to be square root of 2. Light undergoes total internal reflection in the prism at the face PR when alpha has a minimum value of 45 degree. Then the angle theta of the prism is. So we have to suppose to find out the angle of theta, that is angle of prism, and it says that for total internal reflection, the value of alpha is given to us. So So we can just draw an approximate figure for that, and so we have, this will be our normal, so this is our alpha, okay, and this will be our refracted ray. So angle is, let us suppose we have R1 and it strikes somewhere here, strikes here, and normal on this point. Let us suppose this is our, it is given as P Q R, and let us call this as A and this as B, and it will be moving in this direction for total interreflection, okay, and we are going to get this angle will be our, let us suppose, critical angle, that is our theta C, and we have supposed to find out this angle theta, and refractive index is given as square root of 2. So we are going to use Snell's law at A. Snell's law at A, and this will be a refractive index of 1. So we get this as mu is equal to sine of alpha divided by sine of our R1, and mu is our square root of 2, so this is equal to square root of 2. Alpha is said to be given as 45, so therefore we can write that our sine of R1 is equal to sine of 45 is 1 by square root of 2, so this comes as 1 upon square root of 2 multiplied by square root of 2, giving us 1 upon 2. So from here we can write that our R1 is equal to 30 degree. And we also know for a critical angle theta C, you can say for critical angle theta C, we can write that our sine of theta C is equal to 1 upon mu, and the mu is our square root of 2. So we get our critical angle, that is theta of C, is equal to 45 degree. And now we can use just triangular property, and that will be giving us the required theta which we require. Okay, so if we say in triangle PAB, so we have in triangle PAB, okay, and in this triangle we can write that our theta plus 90 plus R1 plus 90 minus theta C will be equal to 180 degree. So we know all the rest of the values. Theta C is over 45, and first of all this 90 and 180 goes away, and we can write that our theta plus R1 we found out is our 30, and theta C we found out is 45, is equal to 0. So this gives us our theta is equal to 15 degree. This is the angle of prism. So option number A is the correct option. Option A is correct. We come to the next question, and in this question it was asked in the year 2016 mains, and it states that excuse me please, and it states that a transparent slab of thickness D has a refractive index of n that is dependent upon z axis rather, then that increases with the z. Here z is the vertical distance inside the slab measured from top. the slab is placed between two media with a uniform refractive index n1 and n2, where n2 is greater than n1 as shown in the figure. A ray of light is incident with angle theta y from medium 1 and emerges in a medium 2 with a refraction angle theta f with a lateral displacement L. Which of the following statements is or are true? So this question is basically, we have, ideally we can say, it is consisting of, we can say, three refractive indexes. Okay, first refractive index is of this slab, which is mentioned as 1. Second refractive index is of this n2, and within these two we have a, you can say, transparent slab whose refractive index is nz. So it is basically combination of three different materials having three different refractive indexes. The slab 1 is having a refractive index of n1, so which is said is constant, doesn't vary. Similarly, the same situation is n2. The only variation in the refractive index is that of the slab, transparent slab, which is between 1 and 2, and its variation is with along the width of the, you can say, the slab. Angle of incidence is given as theta I, and angle of emergence is given as theta f, and it is said the lateral displacement is given as L. Okay, so these are the two, you can say, okay, and so we can say that the transparent media is a non-uniform refractive index. It doesn't have a constant value. Okay, so we start from there only. We are given that the slab has non-uniform refractive index, and that is given as n of z. Okay, and increasing with z. It means as we are going to move from 1 to 2, it is going to increase, increasing with z. And another thing that is given, that the slab is between two uniform media. Okay, so we have two uniform media, and we can call it a top media as well as bottom media. So one is our top medium, which we call as medium 1, and its refractive index is given as n of 1. And then we have bottom medium, we call it as medium 2, and its refractive index is given as n2, and we are also given that n2 is greater than n1. Okay, and the first thing we are going to check about the which of this option is the correct one. Okay, so let easier to identify is with respect to Snell's law. Okay, so let's start with Snell's law. And Snell's law is, you can say, it is, we can apply it with respect to the two boundaries, and so we can say that applied at two boundaries. Okay, and here the ray enters medium 1 and exits medium 2. Therefore, we can say that our Snell's law applies at entry and exit. Entry and exit. Therefore, we can straightforward write that our n1 sine of theta I is equal to n2, and we have sine of theta f. So this is directly from the Snell's law. Therefore, we can say that option number C is the correct one. Option C is correct. Okay. And obviously, the corresponding option which we can see is option number B, which is incorrect because it doesn't follow the Snell's law. So option B will be automatically, you can say, based on this entire discussion, we can further conclude that option B is incorrect. And we can further say that the lateral displacement, that is our what was left. Okay, so we have two things left. One is L is dependent upon n of z and L is independent of n2. Okay. So first of all, let's try to understand what is the lateral displacement. So it is a lateral displacement is nothing but horizontal shift between incident and emergent ray within the slab, and that is due to, we can say, bending of the light inside the medium. This we can say is horizontal shift between incident and emergent ray and within the slab. And so it is measured between the, you can say, ray's original path and the actual emergent path, but it is only limited up to the exit point of the slab. Okay, beyond that there is no meaning of the lateral displacement, okay, because it will be traveling straight forward. So we can see from here that our, because of the basic definition of lateral displacement, the ray gradually bends because of the refractive index of the slab, because of the refractive index of slab. And therefore we can write that our L is dependent on our n of z. So from here option number A is correct. So based on this we can conclude that option number D cannot be correct. So we have this option C is the correct, and we have option D is correct. Okay. Next question. It was asked on the 2060 mains, and it states that a box of pinhole camera of length L has a hole of radius A. It is assumed that when the hole is illuminated by a parallel beam of light of wavelength lambda, the spread of the spot obtained on the opposite wall of the camera is the sum of its geometrical spread, and the spread is due to diffraction. The spot would then have its minimum size, say B minimum, when. So we have a pinhole camera whose length is given as L and radius is given as A. Wavelength is given as lambda. And in the question itself it is given that the spread is a combination of the geometric spread as well as spread due to diffraction. And diffraction spread we know is proportional to lambda upon A. And we have to find out the, you can say, the minimum size of that spot. So we can just draw an approximate figure for that. And we are given a radius A, and we have, so length is given as L, and radius is given as A. So this is our A radius, and L is the length, and it is illuminating the opposite wall, and which is a combination of the geometrical spread and spread due to diffraction. So it will be a combination of both. And obviously this will be our A, and this will be our, you can say, L lambda by A. So it is on the both side. And we are given that the total spread, okay, I think radius is given as A. Yeah, radius is given as A. Let me correct it. So the radius is given as A. So we can say that the total spot size B will be equal to 2A, and this will be 2L lambda by A, and 2A is the geometrical spread and 2 lambda by A is the diffraction spread. So this part is our geometrical spread, and this part is our diffraction spread. And we need to find out the, we can say, minimize B, so we can easily differentiate it, and we can write that our dB by dA, this will be equal to 2 minus, and this comes as 2 lambda upon A square, and is equal to 0. So this tells us that our A square will be equal to lambda multiplied by L, or we can say A is equal to square root of L times lambda, and we can then calculate the minimum value of B. We substitute it, so we get that our B minimum will be equal to 2A plus L lambda by A. Substituting value of A, we get this as 2 square root of L lambda plus 2 L lambda divided by square root of L lambda. and we can rationalize or we can solve it otherwise also. We get this as straightforward will be equal to 2 square root of L lambda plus 2 square root of L lambda. This comes as 4 square root of L lambda. So we got value of B is 4 square root of L lambda and value of A is square root of lambda. Okay. So therefore we get that option number C is the correct option. Sorry, not C, because one second. Let me check whether these options are correct or not, or my calculation is wrong. Because A looks the correct one. Yeah, I think this is correct. Okay. And I forgot to solve it further. That is the last part. We can say that the radius of the spot which we have found out. Radius of spot will be equal to half of 4 L lambda, and this comes out now correct one. Yeah, 4 L times lambda. And now it's okay. Option number B is the correct one. Option B is correct. We come to the next question. It was asked in the 2016 mains, and it states that an observer looks at a distant tree of height 10 meter with a telescope of magnifying power 20. To observe the tree appears. To the observer, the tree appears. We have to find out how the observer is seeing the tree of a height 10 meter. Okay, so it will be either 10 or 20 times taller, or it will be 10 or 20 times nearer. So these are the options. And we are given that height of the tree is 10 meter. Therefore, we can say that angle subtended by tree at the eye. Let us suppose that is theta, and this theta will be equal to tangent inverse rather h upon d. And for small angles we can approximate that will be equal to h upon d. Okay. And now if it is being viewed through the telescope, so you can say viewed through telescope, we can write the angular magnification that is our m will be equal to theta prime divided by theta. And here theta prime is the angle subtended by the image when seen through the telescope. And we are given that the magnifying power is 20. So we can write that 20, or we can say our theta prime will equal to m times theta. So this comes 20 times h upon d. And let us assume that the apparent distance of the tree is d prime. So you can say that the apparent distance is our d prime. Therefore, we can write our theta prime will be equal to h upon d prime. So this gives us that we have 20 into h upon d is equal to h upon d prime, and h and h goes away, so we get our d prime will be equal to d by 20. So therefore we can say that a tree appears 20 times closer. So we can say that tree appears 20 times closer. So the option is 20 times closer, means option number D is the correct option. Option D is correct. Come to the next question. It was asked in the 2016 advance, and it states that while conducting the Young's double slit experiment, a student replaced the two slits with a large opaque plate in XY plane containing two small holes that act as two coherent point sources S1 and S2, emitting a light of wavelength 600 millimeter. I think it has to be nanometer, not millimeter. The student mistakenly placed the screen parallel to XZ plane for Z is greater than 0 at a distance D, which is 3 meter. I think this should be also millimeter. Yeah, this is millimeter. From the point S1 and S2 as shown schematically in the figure. Okay, now this is correct one. Okay, yeah. This is meter, other D is millimeter. The distance between the source D is 0.0663 millimeter. The origin O is at the intersection of the screen and the line joining S1 and S2. Which of the following is or are true for the intensity pattern on the screen? And we are given that there are two sources, S1 and S2. No doubt they are placed on the same axis, but still it is given that they are coherent with each other. Okay. And we can easily find out the path difference at point O because of these two sources. So you can say that path difference at point O difference at O, we can call it as delta x. Then this delta x will be equal to, that is D, which is given as 0.6603 into 10 to the minus 3 meters. And we are going to find out this our path difference in terms of the lambda, and that is going to help us to identify how whether it is a bright spot or for the dark spot, because we know that for constructive interference, let me write it, that we know that for constructive interference constructive interference, the difference should be that delta x should be equal to n times lambda, and for destructive interference, the path difference, that is delta x, should be equal to n plus 1 by 2 times lambda. So we have to reformulate, let us suppose this as equation 1 in terms of either of these two. First of all, we are going to divide it by lambda. So we can say from equation 1, we get delta x upon lambda is equal to, this is our 0.6603 into 10 to the power minus 3, and lambda is our 600 nanometer 10 to the power minus 9, and this comes as close to 100.5. 10 is missing. So it becomes 1000.5. And we can easily see that this can be represented as a half integer. Okay. So we can say that our delta x upon lambda will be equal to 1000, and this will be over 500 plus. So you can write this as 500 plus 1 by 2. I think, sorry, not 500, my mistake, 1000. 1000 plus 1 by 2, because 1 by 2 will be giving us 0.5. And from here we can write that our delta of x will be equal to 1000 plus 1 by 2 and multiply by lambda. So this equation is our, we can say, same, which is for the destructive interference. Okay. So therefore, we can say that point O will be having a dark point, that is our destructive interference. Okay. And therefore, we can write that there will be a dark fringe that will be very close to O. Okay. And it will be also consisting of, you can say, semicircular fringes, okay, that will be centered at midpoint of the sources. So both A and B will be the correct option. So from here at least we can say that there will be dark fringe centered at O. Centered at O. Okay. And in semicircle. So A and B are correct. B are correct. We come to the next question. And it was asked in the 2016 advance, and it states that a plano-convex lens is made up of material of refractive index n when a small object is placed 30 cm away in front of the curved surface of the lens. An image of double the size of the object is produced. Due to reflection from the convex surfaces of the lens, another faint image is observed at a distance 10 cm away from the lens. Which of the following statements is or are correct? Okay, so this is basically refractive index, radius of curvature, image, and the focal length, which we are going to find out. So we are given that the object distance is our 30 centimeter. So we can say our u is our minus of 30, and image distance for refraction, that is our 60 centimeter. Because the magnification is given as 2. Okay, so let me write magnification, that is 2. So therefore I can write that my v1 will be equal to my 60 centimeter, and this v1 is basically my image for refraction. So I can say from here my v1 is my image for refraction, and another image is formed which is a 10 centimeter, that is our, let us suppose v2, and that is our 10 centimeter and that is a image for reflection, image for reflection. And here we are going to use two formulas. One is lens as well as mirror, and then the other are, you can say, lens maker formula and the for focal length formula. So these are the formulas which we can use. So first we are going to use the lens formula, and which states that 1 upon f1 is equal to 1 upon v1 minus 1 upon u. So we substitute the value, we get this as 1 upon 60 minus of 30. So this gives us my f1 will be close to 20 centimeter. Then we can use the mirror formula, and mirror formula is our 1 upon f2 is equal to 1 upon v2 plus 1 upon u. So this comes to 1 upon 10 plus minus of 30. So this gives us that our f2 is 15 centimeter. Based on this f2, we can easily find out our radius of curvature. So you can say radius of curvature, that is of r, will be equal to 2 times f2, giving us 30 centimeters. And then we can further find out a refractive index by using the lens maker's formula. So you can say that we have 1 upon f1 is equal to n minus 1, and we have 1 upon r, and we substitute the value, we get this as 1 upon 20 is equal to n minus 1, and we have 1 upon 30, and this comes as n minus 1 is equal to 30 divided by 20. So this gives us that our refractive index n is equal to, this comes as 3 by 2 plus 1, giving us 5 by 2, which is close to 2.5. So we can just check the option, refractive index is 2.5, so this option is correct. Radius of curvature is not, and the focal length is, lens is 20 centimeter, and the image is, okay, so we have two options, option A and D are correct. Okay, one second. Yeah, so final image, the faint image will be our real and erect. So option C is also correct. So we have option A, C and D are correct. So I think, yeah, so this completes all the questions. Thank you.